morning and good afternoon, everyone, and welcome to today's Optimizing Nutrient Removal in Activated Sludge Wastewater Treatment Plants. This webinar is part of the US EPA's Office of Compliance Technical Assistance webinar series for plant operators, inspectors, and compliance assistance providers. My name is Peter Behor from the US EPA Office of Compliance. My colleagues Laura Paradise, Jake Gwynn, and I will be operating the webinar. We're also joined by Brendan Held from EPA's Region 4 Atlanta office to help answer questions in the Q&A box. This is only our second time using Zoom Gov as a webinar platform, so we invite you to learn along with us as we continue to navigate this platform. Your audio is muted, so to type a question or comment, select the Q&A button on the bottom of your screen, type your question in the box, and then select send. You may submit your questions in the question box at any time during the webinar. The chat box is disabled for comments. However, the presentation slides, presenter bio, and other handouts will be posted shortly in the chat box for you to download during the webinar. If you are unable to download the handout, this information along with the Q&A report will be emailed to all webinar registrants in about a week. This webinar is being recorded for future viewing. It will be posted along with all past webinar recordings to our site. Also, our Zoom Gov license will only allow 1,000 webinar attendees. So if you're joining, welcome. But if you are unable to log in for future webinars, it may be that the webinar is already at capacity. Please keep in mind for future webinars, log in early. And if you're log in or log out during the webinar, it may be difficult to get back in. We found that we allow people to register greater than 1,000 because people often don't attend. So we want to make sure that we're using our full capacity. Regarding certificates, if you're watching this webinar today as a group under the name of one registered attendee, please type the first name, last name, and email address of all persons in attendance into the Q&A box. All registered webinar attendees, along with the added names from the Q&A box, will receive an email certificate of attendance from Laura Paradise in about a week. Please discuss eligibility of continuing education credits with your state's certification authority. Acceptance of certificates for continuing education credits is contingent on your organization's requirements, and EPA cannot guarantee acceptance. Thank you for being with us here. Presenting today is Grant Weaver. Grant is a licensed wastewater operator and professional engineer. He holds a BS in biology and MS in bioenvironmental engineering, completed postgraduate studies, environmental toxicology at MIT. Grant's visited and worked with the staffs of over 150 North American municipal wastewater treatment plants to realize significant improvements in nitrogen and phosphorus removal. I want to thank Grant. This is his third in a series of 4 webinars. Grant, I'll turn it over to you. Thank you very much for your help today.
Well, thanks, Peter. I guess the thing I got to say is the weather must be bad around a lot of the country because, in fact, we're bumping right up against the 1,000 already. So the only reason I can imagine that this many people are tuning in to listen to this guy is must be pretty gloomy outside. I don't know. Well, seriously, thank you so much. Thanks to everybody. Mostly for those of you in the audience for listening in. This presentation's for you. And we've got a great behind the scenes staff that's monitoring your questions, your comments, and they have been instructed this session, as they have in prior ones, to interrupt anytime with any questions or comments. All right, we have 995 signed up, so room for 5 more, and then the rest of the folks are going to luck out and not have to suffer through this today. So what are we doing here? We've got a series going. It's kind of geared towards operators, although I think there's a lot of regulatory interest in this. It's wastewater treatment plants, municipal wastewater treatment plants, not necessarily designed for nitrogen removal or phosphorus removal, yet through some tricks, we're training the bacteria in the treatment plant kind of like a flea circus to get better nitrogen and phosphorus. So I'm sharing case studies to try to stimulate interest in folks to do more with what they already have, maybe in advance of upgrades, maybe even in lieu of some upgrades, get more nutrient removal out of existing treatment plants, oftentimes saving money, as we've already discussed in some of the case studies. So we started the series off in January on oxidation ditches. That's the racetrack style of activated sludge treatment plants. February, sequencing batch reactors. And today, we're going to continue this activated sludge discussion, but we're going to talk about some of the other types of activated sludge. Folks that are getting improved nitrogen, improved phosphorus removal, hopefully stimulate some interest and discussion on everybody's part. And then next month, I'm really excited about this one and looking forward to it. And I hope that there's a lot of dynamic discussion. Undoubtedly, there'll be some disagreement with what I have to say, because we want to put some opinions out there on how do we transition from a permit compliant industry, which is what I've experienced in my career, to one that goes more towards what I'm calling wastewater excellence. How do we get that into our culture? And what's in the way of it? What are the opportunities to facilitate it? So I'll be putting ideas out there and looking for discussion. All right, as always, this is an opportunity for a person like me that's just a tremendous opportunity. I've got 1,000 folks listening. I get to share some of my experiences, some of my thoughts, some of my ideas. They're not EPA's ideas necessarily. EPA's given me the forum to do this, but I'm not speaking for EPA, so, or any state regulator, any regulator at all. So please keep that in mind. If you hear something from me, it's Grant Weaver's opinion, and EPA's given me a forum to share that opinion. So don't hold them to anything that I might say, if you would please. Acknowledgements. How do you begin? Okay, when I visited, in my visits to over 150 treatment plants, much of it's paid for by state and federal folks. There's so many people to thank that have given me the opportunity to get these experiences that I'm sharing with you. Specifically today, I've got, what is that, 6, 7 treatment plants. I'm going to focus in on 4 of them, and then 3 of the larger ones I just want to bring out because I don't want there to be the misconception that this works only for smaller plants. Most of my experience is with the smaller plants, but some of these bigger facilities, Helena, Kalispell, Nashville, pretty good sized plants have seen a significant nutrient removal. So I want to focus in on the others: Conrad, Norris, Parsons, and Sunderland. And of course, thanks go out to the operator staffs of those. Thanks also go out to EPA, who's funding this, been supporting this kind of work, encouraging it and promoting it around the country. And then the state regulators that have been doing likewise in their jurisdictions. And you know what, if I had the time and the opportunity, I could probably put 10 more slides up like this. So many people have made this. We're moving from this being 10 years ago, this was an unusual thing to try to get nitrogen or phosphorus removal out of a plant not designed for it. Now it's becoming much more, I don't say it's the norm, but much more accepted. And thanks to all of these people for making that happen. Today, all right, what are we talking about today? Well, I guess there's no mouse in my pocket, it's me. What am I talking about today? Well, we're going to talk about real quick. The last 2 sessions were very quick, but this is going to be even quicker. And I'll real quickly review biological nitrogen removal, real quickly review biological phosphorus removal. I'm thinking maybe 5 minutes on each. I can give a half-day presentation on each topic, or even probably a full day on each one. So that's pretty condensed. So we're going to move through that and get into the case studies. And as I previously mentioned, it's these first 4 that I really hope I can get through today. That's going to be my main focus. And then with the time that remains, I just want to wade in real shallow explanation of how some of these bigger, more complex facilities, some of the things they've done. And again, a discussion. So questions, comments, I'll have breaks every now and then for that. But Brendan Held and Peter Bauer are there. They're armed and ready to go with interruptions anytime that feel appropriate. When we got 1,000 folks, please don't be surprised if you have a question or comment and we're not able to get to it. But please do know that every typed in question that you put in or comment will be responded in kind. We will follow up with a written response. So please put them out there. All right. Nitrogen removal. So nitrogen removal is a 2-step process. Ammonia is converted to nitrate. Ammonia is converted to nitrate by bacteria living in the wastewater. So part of the mixed liquor, as we like to call them. Bacteria, protozoans, anyway, life forms living in the wastewater. And they do this in an oxygen-rich environment. They don't need organics for BOD, soluble organics, biochemical oxygen demand. They don't need a lot of that to grow and convert ammonia to nitrate. In fact, in a wastewater treatment plant, most of the BOD typically needs to be removed before we have active ammonia removal. And in fact, a great process control tool, because you can get a quickie ammonia removal results in a minute using test strips, or 15 minutes using some benchtop instrumentation. If your ammonia is very low, you know that your BOD is low. So BOD is a test that takes 5 days. So you can find out within minutes how well, if your BOD is down fairly low just by doing an ammonia test. Bacteria are sensitive to pH and temperature, but my experience has been both myself operating facilities and working with other operators. Once you dial in ammonia removal, except for that occasional upset or a big storm that brings in too much flow, ammonia removal is fairly consistent, fairly predictable, fairly controllable. It's the next step with the hardier bacteria that's harder to maintain that consistent removal. And that second step is nitrate removal. So the nitrate that gets produced when the ammonia is removed, it's still a soluble form of nitrogen, it's still in the water, it's still available as a nutrient. So to get that out of the water, we need to convert that nitrate to nitrogen gas. So if you know anything about chemistry here, we're going to pull that O off of the nitrate right over here. Well, we're going to train our bacteria to do that. And how we do that is we abuse them by cutting down on the amount of dissolved oxygen. They're going to want to fight to stay alive. Life forms, we like staying alive, most of us. And they will find the oxygen that's not available as a free oxygen, dissolved oxygen, and they'll breathe the oxygen off that nitrate molecule. They need organics, they need BOD, soluble BOD, and as they grow, they'll convert that, they'll be respiring the oxygen off the nitrate molecule, and that will leave nitrogen gas escaping into the atmosphere. The atmosphere is 3/4 nitrogen gas, so it's not like it's polluting the atmosphere. And as I hinted at, the bacteria that do this are hardier bacteria. They grow faster, they're less fussy, less susceptible to pH and temperature changes. But this is, most every facility, this is the harder step to maintain consistently. And my experience is it's almost always because of an inconsistent amount of BOD to drive the biochemistry here. So those are the 2 steps for nitrogen removal. We got 3 steps for phosphorus removal, and then we're done with the background and we're on the case study. So let's do a little phosphorus, and if there's any questions about nitrogen or phosphorus, I think we'll take a short pause for that, and then we'll get right into the case study. So phosphorus removal, biological phosphorus removal. Of course, you can remove phosphorus using a chemical precipitant. I'm really not the guy to talk to about that. It's not much in my wheelhouse. You can use an iron salt, ferric or ferrous. You can use an aluminum, or there are some rare earth metals now that are gaining in popularity. But you're creating an inorganic precipitant. But that's not what I'm promoting. I'm promoting biology. So we're going to trick the biology. Actually, we're going to cultivate the life forms that will concentrate phosphorus inside their bodies. They're fussy eaters. My analogy is they're like the panda bears at the National Zoo, which I guess have been shivering the last few days, talking to the folks from Washington. Even though the cherry blossoms have been out, it's been cold there and rainy. But if there's no fresh bamboo shoots, the panda bears, they starve. So we found our politicians have been very good about agreeing on maintaining a good supply of bamboo shoots for those panda bears, because we don't want the moms and the children to have a big fuss at the zoo. Well, the bacteria that remove phosphorus aren't as cute as the panda bears, but they're as fussy, and they will only eat a very short chain molecule called volatile fatty acids. It's a category. There's 6, 12, 18, I don't know, half a dozen or so different forms. Vinegar is one of them. Volatile fatty acids is almost methane gas if you have an anaerobic digester. If you have an anaerobic digester and do the acid alkalinity ratio, this is the acid. So we've almost totally brought this organic material to methane gas. So if you know much chemistry, there's a very few carbon molecules. It's a short chain. It's very easy for most life forms to eat. So it's a preferred food for a lot of life forms, but it's the only food for the bacteria that remove phosphorus. So we got to create that. And we create that in septic conditions. That was long-winded. Also in septic conditions, we've got to introduce the bacteria that are going to eat these volatile fatty acids. So really little to no oxygen in an environment. Create either in the same tank or in a different tank, but you got to bring that volatile fatty acids together with the bacteria in low to no oxygen environment. And when that happens, the phosphorus removing bacteria, the $10 name is PAOs, or phosphate accumulating organisms. I've dumbed that down because I don't like that phrase, so I call them BioP bugs. So the BioP bugs will eat the phosphorus in this low oxygen conditions. They don't grow, they just become energized. It's kind of like Grant here in his elder years, the waistline's getting bigger. So they get energized on the volatile fatty acids, and then when they migrate into aerobic conditions, or their conditions change to aerobic, these bacteria that have been energized under aerobic conditions, they will multiply, and as they multiply, they'll suck phosphorus out of solution. So for biological phosphorus removal, we need to be aware of these environmental conditions that the bacteria thrive in, and provide them. That is, if we're going to control it. And the same for nitrogen. So there's a little background, and that is basically what I wanted to do as far as an overview of nitrogen and phosphorus. I don't know, Brendan or Peter, if you have any questions or comments, I'd be happy to take those before I go into the main show here, the case studies.
It'll be up. Brendan,
Yeah, sure. So there's just a couple sort of related questions about the limits of the nitrification process. One related to temperature, asking if there are bounds on nitrification as far as temperature goes. A related question about being able to nitrify most of the year, but winter into spring, it's almost been impossible to nitrify. Is there anything we can do during that time period to increase nitrification?
Okay. I'm a guy that doesn't much, I'm going to share numbers throughout the presentation, but I don't like to be constrained by them. And so please, I'd urge anyone listening in to feel the same way. Don't be constrained by what's norm or typical. Because I've worked with plants in Montana, and Montana's cold everywhere in Montana, but way up on the northern, on the Saskatchewan border, and they're nitrifying year round. In fact, worked with 34 treatment plants in Montana, and I think every one of them nitrifies year round. And up in the northern, they call it the highline area of Montana, they get minus 20-degree weather, not occasionally, every winter. So the bacteria can survive in low temperatures. I myself have experience running plants that get down to about 5 degrees Celsius. And some of these Montana folks told me it's gotten as low as 2 Celsius. But it is very problematic if you lose ammonia in the spring. It can take a late winter to try to get it back. My experience is it takes until it gets up about 18, 20 degrees Celsius before they'll return the ammonia removal. So you can maintain it in the winter, but if you lose it, it's very hard to get it back. Anything else?
Yeah, a couple questions related to VFAs. One, does the digester supernatant contain VFAs? And 2, which bacteria are generating the VFAs?
Okay. I'm not a microbiologist, and I could look that up and tell you, but I don't know which bacteria are. I call them BioP bugs. So they're the bacteria that remove phosphorus. Smarter people call them PAOs, phosphate accumulating organisms. I'm sure there's genera and species we could put out there, but I can't answer that. The digester supernatant contains very little volatile fatty acids because the volatile fatty acids have been converted to methane. So anaerobic digesters, the decant or supernatant coming out of those, kind of problematic for phosphorus removal because there's been phosphorus release in the solution, but there's very little volatile fatty acids available to energize those the PAOs, the BioP organisms. So that's pretty bad fuel, but supernatant from a digester, well, I'll get into that later. I've got some examples that I think will be of real interest to that question. So anything else?
Brendan, yeah, I'm going to launch the poll question while Brendan asks if he has the last question too.
Oh, you're going to launch a poll. Wow. Okay.
Is that okay?
Of course it's okay. You're the boss. I'm just hired help there. You know, loving life. So.
Well, so I'll just ask this question because I think it'll probably make a good segue. Are there facilities with phosphorus limits using BioP removal to achieve compliance? We typically only see chemical removal of phosphorus.
Okay, that's a great question. You know, I'm glad that was asked. And the answer is an emphatic yes. I'm going to stay with Montana in answering this. There are several plants in Montana, Kalispell, Missoula, Bozeman. I think Billings just made an upgrade. I'm probably leaving some out that are purely biological, no chemicals. I know in the case of at least 3 of those, they're getting typically a 0.3 milligrams per liter of phosphorus. No chemical, they're using filtration. I think at least some of them are, maybe all of them are. But yes, and then I've got a case study today that's a plant not designed for phosphorus removal, biologically is getting the same kind of numbers. So it can be done. And I had 2 examples today of that. So that was a great question. the answer is yes. And chemicals are expensive, and chemicals, they have their environmental impact. So if it can be done biologically, that's what I'm trying to promote. So we got the polling question going.
Yeah.
Good response. Peter, go ahead.
No, are you able to see it, Grant? And you can just read off it. I don't have to interrupt.
Okay, just tell me when you're ready to close it, and
I'm going to close it in 2 seconds. We've gotten about 70%. All right, I just closed it. Share.
Okay. Okay, we've got, what do we have here? About half of the, 2/3 of the, almost 3/4 of the people have a pretty good understanding of either nitrogen and or phosphorus, and then about 28% are saying not so much. So for those of you without a pretty good understanding of it, these are going to be opportunities, these case studies, and there are, I'm going to show some slides here coming up, bringing back the EPA's training classes, webinars that are available. I just offer those as opportunities to increase your knowledge. So let me click the stop sharing on that. And what did that do? Didn't do much. Okay, so I'll just continue on with my slides. Peter, I don't know how to get this out of the middle of my, oh, there it is. Okay. Well, for everyone, I hope this is of interest to you. Well, there's the first polling question. So with that behind us, regardless of your knowledge level, I hope you find these case studies to be of interest. So let's begin. Oh, before I begin, here's where I've had the good fortune to travel around the country. In 2 weeks, I'll be going to Washington State, visiting 6 or 8 treatment plants there. But this is my experience, and it's really standing on the shoulders of the people that operate these plants, learning from them, maybe pitching some advice to them, giving them some support. But the successes are because of their good work. So I want to start with a plant that actually was featured in a magazine about 6 or 7 years ago. I've got a link to that article. Somebody's unmuted there that had some noise in the background. Sunderland, Massachusetts. And I wanted to start with this one because it's really a very non-complicated. I didn't want to say simple. It's not that complicated, not a lot of moving parts to this treatment plant. As you can see, it's about a 500,000 gallon a day, about 500,000 gallon per day design. It's operating about half that flow. Bob Gavery, who had been the operator there for 30 years. I don't know, he just one of those guys that when I stopped and talked to him, he says, I'd like to try that. And so the treatment plant to be described is 2 aeration tanks, activated sludge, mechanical aerators, very straightforward, 30, 40-year-old treatment plant. No primary clarifiers, secondary clarifiers, disinfection, and then sludge holding. And the sludge is wasted into, I'm pretty sure these are the sludge holding tanks. And the sludge, I haven't been there for 5 years anyway. And the sludge is just decanted and then hauled away as a liquid. That's pretty common in the Northeast. A lot of treatment plants have no dewatering equipment, and the waste sludge, which of course are the dead bacteria from the aeration tank, they're just hauled away for dewatering and treatment elsewhere. Straightforward treatment plant has no nitrogen limits, but right over here is the Connecticut River. And the Connecticut River flows into Long Island Sound, and there's been a lot of interest in Long Island Sound on reducing nitrogen. So Bob knew that the day was going to come when Sunderland, Massachusetts, would also need to reduce nitrogen. So using the technology of the sequencing batch reactor, which we talked about, was that last month? Yes, last month, early last month. It was almost 2 calendar months ago. Cycles the air on and off in the aeration phase. Raised his biological concentration, his mixed liquor concentration a bit, and started cycling the air on and off. Cycled it on long enough to get that ammonia conversion to nitrate, that first step I talked about, and then off long enough, and by long enough, I mean enough consecutive minutes for the dissolved oxygen to deplete. No mixing, it just settled out in the aeration tank. Flow continues to come in and through the aeration tank with the aeration, the mixers, the aerator turned off. And the dissolved oxygen would drop to the point where the bacteria were needing oxygen bad enough that they do the work to breathe the oxygen off the nitrates. And as they do that, the nitrates are converted to nitrogen gas, literally bubbles out of the tank, looks like little raindrops, the bubbles coming up to the top. Sometimes you see some big ones. And the nitrogen gas goes to the atmosphere, so there's no more nitrogen or very little left in the effluent. Simple as that. Science was, as Bob says in this article, kind of refreshing my memory, took him a couple months to dial in the air on or air off cycles. He had to buy a timer for his control panel so it would automate the air on and air off. And he bought an ORP, a portable ORP, so he could measure what the oxygen reduction potential is in the aeration tank. It's an alternative means of measuring the oxygen. To me, it's a preferred means. I talked a little bit about it in my prior webinars. It's a great tool for checking the environmental conditions. So there's Bob smiling away. Had some inline instruments put in later as this thing started to be a success. Very interesting. It's a contract operated facility, and they had such a strong relation with their community that they said, let's try this. Let's spend a few $1,000s in advance of any regulations. And if we can make this work, maybe you won't have to upgrade this plant when that inevitable happens and the total nitrogen limit is put into place. And sure enough, Bob was able to drop his nitrogen to about 1/3 of what it had been. There really wasn't any impact on phosphorus, no effort made for phosphorus removal. So he raised the biological concentration, the mixed liquor, suspended solids. He cycled that air on and off, and he bought some instrumentation and saved money on electricity, right? If your air's off and you're not running the motor that runs the mechanical aerator, then you're not consuming electricity. So he also felt that he got better solids compaction, so that he had was easier, and because of the older sludge age, he got a little bit of endogenous respiration. He got some breakdown of the cells in the aeration tanks that are a little bit less sludge, a little thicker sludge, and avoided or postponed, if not outright avoided, a facility upgrade. Very happy with the results with his efforts, and yes, it took more effort on his part, and it's kind of fundamental to pretty much every one of these. There's more work involved, but it's more fun work. There are very few places that I've been that after they've implemented some nutrient removal, that they almost inevitably say it's more fun to come to work, and there's a better relationship between the staff because they're often all in it together. You can see this is about 8 years ago when this all happened, and it was starting out up in this area, total nitrogen in the 20s area, and then dropped down on average to about 8. So there's the story. If you want to look it up, here's how you can find it, or you can simply use the search engine. You know, if you want, you can pull out your phone and take a picture of the slide, then you don't need to write it down. or you can just jot down TPO magazine, Sunderland, Mass. And if you put that in a search engine, you can get more information on that. So I wanted to start with that. Now we're going to get a little more complicated by the time we get to number 4, 5, and 6 here. Any questions or comments coming in on that, Brendan or Peter?
Yeah. Couple of questions about figuring out how long to leave the aeration off. And also, was that the entire tank or just part of it?
Okay, let's do this. It's the entire tank. It's a mechanical aerator that's just right here in the middle. And by a mechanical aerator, there's a motor sticking straight up in the air. There's a vertical shaft going down through this concrete structure. And then below it, it's kind of like a router blade or a blender blade, and it's partially submerged in the water. And so when the motor's on, it just whips the top of the water. And as it whips the water, it induces air into and mixes the contents. So it aerates and mixes it. So there's no partial part of the tank here. I guess you could do one and not the other, but there's 2 parallel trains. So the entire thing is going air on and air off. Now, how do you figure out how long to have it on and off? There's tools. You can monitor the dissolved oxygen. You can monitor this ORP I've talked about. Love to get into a discussion on that, but I think it's going to take us on a 10-minute side tour here that I'm going to try to avoid. You can monitor the ammonia using a benchtop instrument or a test strip. Pretty quick with a test strip. They're cheap. They're $1 a piece and pretty darn accurate, plus or minus a milligram or so. So you need the air on long enough so that your ammonia is low. And what's low? Low is subjective word. If you have no permit limit, below 2 is low. If you have a limit of some number less, it's got to get down to whatever that number is. You might, if the number is less than 2, you might want to be monitoring this with a more sophisticated instrument than a test strip, a benchtop instrument. Then you leave it off long enough that your nitrate drops. So when you begin this, of course, you got to populate the treatment plant with the bacteria. So it takes a few days in the case of nitrogen, that's all, to populate the bacteria. With phosphorus, it takes weeks. So you start out slow, turn the air off, maybe for an hour in the morning, an hour in the afternoon. You do that for a week, you get used to it. You get everybody at the plant used to it. Probably haven't saved any, haven't done anything for nitrate removal, but you cut your electric bill by almost 10% already. And you're maintaining ammonia removal. Then when you start to stretch that air off cycle out to about an hour and a half or 2 hours, it's typically what it takes to drive it into nice anoxic zone so that those denitrifiers and nitrate removing bacteria will populate. So then that would be the second step, is to expand that air off time up to an hour and a half or 2 hours. And then you start shortening the air on time. And of course, you've gone too far when you start to get an ammonia jump. So if you have an ammonia limit, you got to be more careful about that than if you don't have an ammonia limit. If you don't have an ammonia limit, you can take a little more risk by moving your air off cycle, your air on cycles. Start at 6 hours on, down to 5 hours. And then eventually you'll find a sweet spot, and then the weather will change, and then it'll be winter, and you'll have longer off cycles and shorter on cycles, maybe because of the solubility. But all kidding aside, that's a good progression to go through. And once you're there, it's not locked in. There are going to be seasonal changes, and if there's a significant change in your waste load, that will also have to be accommodated. Now, all of this said, when the storms come and your peak flows go up to 5 times what they normally are, a lot of things need to change. You may need to keep your air on much longer during those periods. Long-winded answer, hopefully that helped.
Grant, I'm going to give you first a time check. We're almost midway through the webinar already.
Okay.
And I know that you're not midway through your slides. I'll just add one comment here, and I know Brenda wants to add one more, but we'll move on. There is a, well, it just scrolled away from me. One viewer here has indicated that the local utilities remind people that electric utilities can provide help with buying instruments and control to implement these changes and helping to save energy.
Good comment. Okay, great. And
Brenda?
thanks for the time check too.
Okay.
Shall we just move on to the next one then? And we'll.
Yeah, I think, Brenda, hold anything till later. We'll keep your answers a little briefer, I think, to move on.
All right, I'll try that. I just love hearing myself talk, and I can't, I'm sorry. So Norris, Tennessee, another smaller plant, older plant. Very little's been done with the plant since the 1970s, except they staffed with a really talented team in Norris, Tennessee. Norris has got Tony Wilkerson and Doug Snelson taking care of the treatment plant. So this is a, oh darn. Oh yeah, I think I have it followed up. So there's Tony on the top and Doug at the bottom. It's a plant not designed for nitrogen removal. Unfortunately, they never measured what their effluent nitrogen was until they were really getting this thing dialed in. So they're consistently now at 6, thereabout. I suspect it was over 20 before, but I don't know. We don't really have the data. They're spending some time working on phosphorus removal, a fair amount of energy. Haven't really got it yet, but I want to tell their story because they've made some improvements, and I think there's some interesting things to learn from this. For nitrogen removal, they raised their mixed liquid concentration. They cycled the air on and off, just like the story I just told you. This is a diffused air. It's a slightly different configuration. I'll show that. For phosphorus removal, they've worked on a fermentation zone, and they've worked with a really talented operator who works for the state, works for the University of Tennessee, named Brett Ward. Brett went out and gave him some great advice and helped them bring their phosphorus level down even more. Very little in cost, but some time monitoring what's going on there. So let me explain if I can. This is a precast, or not precast. It's a package plant. It's plate steel. It's got it was designed with aeration around the perimeter, and actually was designed to have one cell that was the old sludge holding tank, aerated sludge holding tank. I guess it'd be an aerated digester, and the clarifiers in the middle. Got a little catwalk going across. So the wastewater comes in and goes around the outside. It goes into the clarifier. Clarified wastewater is disinfected and then off to the receiving water. Norris is a really cool place. It's where the Appalachia Museum is, and it's a Smithsonian institution. It's affiliated with the Smithsonian. It's north of Knoxville, really neat place. Small though, small service area. So what these folks did for nitrogen removal, they raised their biological population, and they cycled the air on, and you can see over here where one of their settings are typically on for 2 to 3 hours and off for 1.5 hours to 2 hours, and they monitor it every day and make changes every, I don't know, not that often, probably once a month or so, based on seasonality as to what their cycles are. Pretty simple, straightforward, requires an understanding of cause and effect. And that's how how do you learn that understanding? By hands-on. Here's their numbers now. You can see, get a little bit of spikes every now and then. Has no limits for nitrogen. It's just pride, ego, and a care for the environment to try to do better. Phosphorus has been an interesting story. some guy from Connecticut, that would be me, came down and said, hey, I got this great idea for phosphorus removal. Why don't you go buy a couple of these totes, chemical totes, these cubes, IBC totes, are about 300 to 350 gallons each. They bought 2 used totes, and they pumped sludge into the totes. They let it sit there for a day or 2, and then they would dump it back into the treatment plant. The idea being that during that day or 2, conditions would go septic. As it went septic, it would create the volatile fatty acids. As the volatile fatty acids were produced, the mixed liquor, the biota that got pumped in there, would be there, and they would become energized by eating the volatile fatty acids. Then these energized bacteria, when they got dumped back into the plant, would remove phosphorus. Well, that kind of worked, but kind of didn't. So they had better days, better months than others. So then Brett Ward came along and he says, let's try this. Here's a better idea. Let's take a zone, and I did this in my kindergarten art school quality of drawing here. And let's turn the air off in that zone all the time. Let's pipe our return sludge so that it goes around that, so that our influent goes into this no oxygen zone. They open the air up maybe once a day for a little while to kind of resuspend what's in there, but other than that, it's basically sitting in there. And then it's seeded with bacteria that are backfed from the aeration side. So that's providing the bacteria. So this zone is a fermenter, creating the volatile fatty acids, and the bacteria are seeping back in. The wall in between here is very, there's big holes in it. So the aerated side just moves some of that flow in. So that gives enough bacteria to consume those volatile fatty acids that are produced in those septic conditions. And a percentage of the return sludge is being sent into the zone here. Just click that off. Then the third phase, what they've been working on, and I haven't checked in. I should have checked in right before this webinar. They were doing a combination. They were going to ferment a little bit here and then dump it into this zone and see if they couldn't get the best of both here. So here's what we see often with folks that are doing biological and don't yet have full control. We're going to see some great months. And look at that, more often than not, these are going to be winter months. Generally, we're going to get lower phosphorus numbers in the winter, and our struggles are going to be in the heat of the summer, kind of tapering into the fall, kind of the August to October, November time frame. And sure enough, this is what's going on in Norris. So working overall, though, it's trending down. We got a little bump going up here, but the overall trend, and you'll see this in my graphs. I should explain this. The bars are either the monthly, or if they're only doing quarterly, those are going to be my bars. And the black line is going to be the average of the prior 12 months data. So that would be called a rolling 12-month average. So there's the Norris story. I think that's it. Yep. Are there any questions or comments on that? And then we're just going to get ever more successful, maybe more complicated, more, to me, a little more interesting kind of studies as we get with the next couple case studies. But any questions or comments on that?
Yeah, just a couple general questions that kind of highlight a really common concern when we talk about shutting off aerators, and just wondering about impacts of settling solids, particularly on fine bubble diffusers.
Grant Weaver's opinion is mixing is crazy, way overrated. If you can turn the air off and have some loss of mixing, then you're actually concentrating the bacteria in a zone, which means it will go anoxic or deplete the oxygen even faster, which makes that zone even more viable, as long as you don't short circuit the flow around that zone. As far as the diffusers, I've heard that argument. I just threw up there 150 plants I've worked with. I've never had anybody say they've ever had any problems with plugging of their diffusers because of the air cycling on and off, even in tanks that are 20 plus feet deep. So I hate to say that's a myth, because having said that, maybe there'll be 5 or 10 people that will share some experiences. And if you have some bad experiences, please do. But I've never encountered it.
Thank you. Couple specific questions. One is, why do you think it was better in the winter versus the summer? And 2, do they digest solids? And if so, how does that impact phosphorus removal?
Okay, yes, they have aerobic digester, and they have they do decant side stream. That the plants that have that and manage it, as long as you have enough bacteria in your basin to eat that extra phosphorus, you can do that. So it's the slugs that are going to be problematic. So try to make that as consistent as possible. Why does it work better in the winter than the summer? I have some theories, and at the end here, we can get into that if there's time, but it's pretty universal. And I believe that there's the short answer is just a shortage of BOD getting into the aeration zone, and we're just not growing enough, having enough BOD left to grow the phosphorus removing bacteria. But that's one man's theory, and haven't really had anybody sign on to that one yet. We could talk about that in depth, and I think in a phosphorus discussion, that's an appropriate discussion. We just don't have time to go too far with that today. Anything else?
We can hold the rest of the next one. Thanks.
Okay. I think what I'm doing, yeah, another polling question here, and maybe Peter, while you're doing that, I can run through a couple slides while you're doing that. So.
Yep, go ahead, Grant. It's up.
Okay, good. So this polling question, of course, is the heart of what I'm pitching here. Is I kind of am I talking to people that are interested in this, or just kind of freak you out? This whole idea of operating plants differently than designed. I don't know that I can go to the next page without screwing this up, so I think I better wait. What I'm going to follow up with, I'll just chat about it, give a preview, a pre-non-view.
I think you probably could go to the next page if you needed to.
I clicked on this and hit advance. Oh yeah, I can. Okay, so you got both in here. Okay, so one of the ways you might have signed up for this is off of EPA's web page, and it's a pretty long URL over there. So you can, if you want to look for it, you can search EPA Technical Assistant webinars. Really nice tool. And every month there's going to be more webinars added. So you can sign up for live ones like today if you're watching live, or if you're watching a recorded version, or even if you're watching live, you can go and sign up for some past webinars. And as you can see at the bottom, as of the date I did this, there were 26 different webinars. They're all free. And they're typically, I think, pretty much at this hour and a half that we're targeting for today. We may run over a little bit, but we'll pretty much wrap it up at an hour and a half. So it's a great resource, and I just encourage you to take advantage of it and bookmark it if you don't have it bookmarked, or great way to learn more at low cost on these crummy weather days when you want to sit inside and take a break. Okay, we've got a polling. Are you ready to end this poll, Peter?
Yeah.
Okay.
Yeah. Can you see the?
Yeah, so let's see. A percentage, almost 50 people saying that you should operate your plants as they're designed, which you 50 are my enemies. And then different percentages of you have different type of regulatory oversight over to how much flexibility operators should have in your belief system. And I thank you all for answering this. This actually is going to be the genesis of next month's webinar. It's this very issue. How interested are we in the giving control to operators, and what kind of parameters should there be? What kind of encouragement and support? So I'm going to ask that I get this information when this webinar is over, so I can remember these numbers. This is good stuff. Okay, let's continue on here, and I'll find the right place to click. Right, that should have disappeared from everybody, and let's get into our third case study, which is Conrad, Montana. We've got about a half an hour left, right, Peter? Conrad, Montana. Really interesting case study. So this was a lagoon, and then the lagoon, part of the lagoon was made into an earthen-filled, earth wall, extended aeration basin. And then following that is conventional concrete clarifiers. First winter, so I was told, after this was built, there's a lot of icing, caused some serious damage to the clarifier. So this floating cover was put on top of the aeration base. And then once that was done, that worked. It kept it warm enough so that the moving water through the clarifiers, even in significantly sub-zero weather extended periods, they didn't have the icing problem as before. This is an aerated digester, also earthen filled, and underneath here is a building where the preliminary treatment and disinfection occur. Off to the left, these are sludge drying beds. So this plant was designed for ammonia removal, but not total nitrogen removal, and certainly not for phosphorus removal. So notwithstanding the fact that it wasn't designed for total nitrogen removal, Keith Tott, who's the operator here, great guy, and crazy flaming red hair and a wild lumberjack beard on the guy in the winter months, came to the first class. We had a 2-day training class in Helena, Montana, and Keith came, and we had at the end of each class, the 2 days, we talked about people's plants. He talked about his plant, and I said, Keith, what do you think about the idea of trying to shut your air off in your aeration bases? And Keith said, I'm fine with that. I'd like to try that, but it gets to minus 20 degrees here, and I'm not sure I can suck in minus 20 degree weather to restart the diffused air blowers, the intakes on this. So we contacted the manufacturer, and they said, sure, they're going to work. So Keith started cycling the air on and off, and with time, he found the sweet spot and got very good nitrogen removal. Now, the air that cycled on and off in the aeration basin also cycles on and off in the aerated digester. So the sludge, the concentrated sludge, is also getting cycles of air on, aerobic cycles of air off. And as it goes air off, it goes septic back in this basin here. And as it goes septic, creates those volatile fatty acids we're talking about. The bacteria in here are waste sludge from the aeration basin, right? So they're there. If there's enough population with time of the phosphorus removing bacteria, they would eat the volatile fatty acids. So then we asked Keith to start sending some of that bacteria, not the supernatant, but the actual sludge, back into his aeration base. So he sent back about 10% of the sludge that he wasted from the aeration basin into here. It would sit here, and then he sent about 10% of it back. And as he did that, he was sending back energized bacteria, energized phosphorus removing bacteria. And when they hit this tank, they grew and they pulled phosphorus out of solution. I hope that makes sense. So that's what we're talking about for process changes. I don't know. I can't believe he spent $5,000 on lab equipment. Bought some pretty simple lab equipment and got his boss's approval to spend at least an hour every morning, the start of the day, doing process control at the plant. Because in these small communities like Conrad, when the weather's good, they're out doing road work, or they're reading water meters, or they're doing something. And Keith is able to spend at least an hour a day tending to his treatment plant, doing some process control, and he monitors the phosphorus and nitrogen through the plant. And look at these results. Okay, these are quarterly samples, so you see 3 are the same. I just repeated the quarterlies. So the rolling 12-month average after this 2-day class, within a year or 2, had dropped his total nitrogen from just under 30 to bouncing around between 5 and 10. All the while saving money on electricity. But here's the key part, and here's where those 50 of you say a plant should always be operated as designed, where I disagree with that. This plant was not designed for nitrogen removal, was not designed for phosphorus removal, and if it was operated as designed, would not remove nitrogen, did not remove phosphorus. Now, this plant is averaging less than 0.5. So that earlier question about are the plants that are doing it biologically? Here's one. Wasn't designed to, but through a goodly amount of good luck and good fortune and operator dedication and interest and knowledge, tendiness, willingness to try things, got a treatment plant that's producing 5 to 8 milligrams per liter nitrogen and way less than 0.5 of total phosphorus at less operating costs than when he was producing a phosphorus of 2.5 to 3 and a total nitrogen in the 20s. I'm a big fan of Keith Todd and the work he's done in Conrad, Montana. Any questions or comments about that?
Yes, we got a good number here. First is, how long would they keep the wasted sludge in the digester before returning it to the aeration basin?
Okay, it varies because in a lot of these cold climate facilities, they don't waste much sludge in the winter. But there's a lot to that question. If you don't hold it long enough, it won't go septic enough and you won't create it. If you hold it too long, you actually get too much phosphorus release. So there's a sweet spot in there, and it's very case by case. But shooting from the hip, the sweet spot would be anywhere from a matter of a couple weeks to a couple months would be the ideal. And if you weren't getting great numbers, then I'd be, and you were outside of those parameters, I would look at those parameters as a possible cause. Next.
Yeah, thanks. There are a lot of questions. I just want to remind everybody that there are 1,000 people here, so not every question is going to get answered live. But would this similar procedure work in a lagoon?
I don't think so. No.
Let me, while you're looking, Brendan, let me add that Laura Paradise will send out the responses that Grant gives us for the questions that haven't been answered already. And so you will see that and get answers to your questions because Grant has agreed to do that for us.
I agree to do that when they're 300. No, I'll do that. It just may take me a little longer. Yeah, one thing I would like to say as well, I'm promoting the opportunities for operators, and I don't want, and I challenge operators to do more, but I want to caution those on the regulatory side. We're talking A students here that are getting great work. We can't expect this of all plants. We should encourage it, we should support it, but we shouldn't expect it. I just want to put that out there. Brendan, you got another comment or question?
Yeah, there are a lot coming in, so I'm trying to keep up. But another person was wondering how we measure or quantify VFAs.
Typically, I don't. Typically, I use an alternative, and so I look for if it's going septic enough to create the volatile fatty acids. I'm looking for a phosphorus release that happens during those septic conditions. It's some crazy quirk of nature that when the bacteria eat the volatile fatty acids and become energized, that they release phosphorus into solution, and they release it at a very nice ratio of about 3 times. So whatever the phosphorus concentration going into that tank, vessel, container, basin is, about 3 times as much on the effluent side means that you're creating the volatile fatty acids and that the bacteria population is there to consume them. Having said that, you can measure volatile fatty acids. The spectrophotometers have kits for that. There are people who have more sophisticated plants that are designed for phosphorus removal. They will have a target. The kind of numbers I've heard is they like around 250 milligrams per liter of volatile fatty acids in their VFA-rich feed that's going into their mainstream fermenters. But typically, I'm looking for that phosphorus release as my process control tool. Should we take more, or should we move on to the next one? What do you want to do?
I think we should move on and take any remaining time we have at the end if we have time.
Okay.
Answer questions.
All right, let's do this. This one is another amazing story. This is Parsons, Kansas. Parsons in southeastern Kansas. I grew up in Kansas, so my sister-in-law grew up right outside of Parsons. It's totally coincidental. So Parsons, let me get this banner out of here. So you can see it's a population of just under 10,000, about 2.5 million gallons per day design. There's a lot of stuff in this picture. Let me tell you what you're looking at. So all of this in the middle is the old plant, okay? Trickling filters, no longer used. Trickling filter, no longer used. Some clarifiers, no longer used. Over here are digesters. They're kind of silo-like digesters, so they're sticking tall out of the ground. And then over here, this is now the heart of the beast. This is a technology, and they call it a continuously sequencing reactor. This is what their website calls them. It's a pretty cool arrangement. I don't think I'd really want to operate one. I never have. What they have is a donut, as you can see here, is the aeration basin. These are concrete poured in place tanks, and in the middle is a clarifier. Sometimes these have the clarifier in the middle, and sometimes the clarifier is separate. But in this instance, this application, the aeration basin's on the outside. Now you may notice the catwalks here are kind of pointing in weird directions. So what happens is there's a rubber tire right here. And the rubber tire rides on the top of the concrete. And there's a center pivot. And there's an aeration header that goes out. And there's diffusers that are dropped into the wastewater here. And this thing moves around the tank at a rate, I haven't timed it, but I would call it a brisk walk, so that it goes all the way around the tank. I would guess within 2 minutes. I don't know, might be 3 or 4, might be 1, but it's pretty fast. And it keeps moving around and around. And as it goes around, it aerates and mixes the tank for a cycle. And you program that on a PLC or on a SCADA touchscreen. You program how long I want to be in an aerobic cycle. And then it goes and it maintains a target dissolved oxygen during that cycle, so that if there's too much oxygen in the water, even though it's on the aeration cycle, there'll be it might go a few laps without any air getting pumped into the wastewater, and then it'll come back on. It's trying to maintain a target. And it'll do that for an hour and a half, 2 hours, whatever your time here is. And then it'll continue going around with a mixer, mixing device, submersible pumps to mix. And during that cycle, no air is added. So it's designed for total nitrogen removal, not designed for phosphorus removal at all. Now, in the case of Parsons, they operate their digesters differently than any place I've ever seen. And I'll tell you, I think maybe more of us need to operate our digesters like they do. How their digesters are operated is they too cycle with the air on and off. So the air comes on, the air goes off, and it's totally independent of what's going on over here. So it's an aerobic digester, but not always. So I don't know, maybe half the day the air is on and half the day it's off, but I don't think it's off for 6 or 8 hours at a time. It runs off maybe 4 to 6 hours. All 3 of these are being aerated at the same rate at the same time. But again, it's nothing related to over here. Okay, so that's the background. To waste sludge, sludge is wasted around the clock at different rates, at different times, depending upon their wasting rates. And it goes into these digesters. Oh, one thing I forgot to mention. So the digesters all 3 are equipped with overflows. Right, you're familiar, those of you aren't familiar with telescoping valves. So a telescoping valve has a fixed outer sleeve and an inner sleeve that goes up and down, telescopes up and down. And at the top, there's a big V cut in, a V notch, so that as it goes down, obviously it goes up and down, it adjusts what the overflow level is in the tank. So typically, folks operate those so that the overflow is above the water elevation while it's aerating, and then periodically, once a week, some periodicity, the air will be turned off for an extended period of time. The sludge is allowed to settle, and then that telescoping valve is lowered, and it pulls the cleaner water off to go back into the headworks. In Parsons' case, they leave them parked. So sometimes when the air's off and they're wasting sludge, they're displacing, they're putting the supernatant or the decant water out. At other times when they're wasting sludge and these are being under aeration, they're blowing solids right back to the headworks. Now, why would I suggest other people do this? Because for phosphorus removal, when the air is off, creating aseptic conditions, creating volatile fatty acids, the bacteria are getting energized. If you're only sending back the supernatant, you're not sending the energized bacteria back. You're only sending the decant, the cleaner water, the water that's relatively free of bacteria. So you're not, those bacteria that have gotten energized, they're doing nothing for you because you're going to dewater them. They're staying in these tanks. However, in Parsons' case, they're mixing them up and they're sending them back in. So that's allowed a very nice population of phosphorus removing bacteria to develop in these tanks and to migrate back into the aeration phases. So I visited this plant, and it was one that was assigned to me to visit by the state under a contract I have with state of Kansas. And I thought, oh, I don't know, these folks have already got great numbers. I guess it's going to be a learning experience. I had no idea what a learning experience it was going to be. Let me get through these and I'll show you the numbers here. Oh, I had my slides to show you a close-up of that. So the nitrogen, which the plant's designed for, is quite good. Running around 6 total nitrogen. The phosphorus, which I described, here's the aerobic digesters. So it's not designed for it. They don't add any chemicals. This kind of writes up just what I described, or I attempted to describe. I just got ahead of myself. And here we go. Plant not designed for phosphorus, it's getting effluent again, very much like Conrad, which is those of you with familiarity of kind of phosphorus removal. To get below 0.5 with consistency, even using chemicals isn't all that easy. To do it without chemicals and to get it half of that is remarkable. Now, I'll tell you what, Derek Clevenger and his staff are doing a real lesson, I think, for all of us. And I want to apply this, the whole side stream phosphorus removal. Been working with a couple other plants, see if we can get them to do the same or they can find the same. The influent total phosphorus average is 6.8. So that's pretty much right smack in the norm, maybe a little bit on the high side even of influence. So it's not a matter of a weak influent phosphorus. It's a matter of creating a fantastic environment for biological phosphorus. Okay, I really wanted to get that story in. I'm glad we did. We've got 10 minutes, plus I'll go over a little bit, but got 10 minutes for questions on this and the previous ones. And then I just wanted to run through and I'll just want to show you that this same kind of approach can be applied to big plants. So Brendan, what do you got for me?
I see Peter's unmuted too. Did you want to say something, Peter?
No, go ahead. I was just gonna push out the poll question when Grant was ready. All you.
Okay,
why don't you do that?
Well, he's doing that. There's a couple of general questions about filaments. Do you know if any of these facilities had issues with filaments while they were trying to implement phosphorus removal?
Yeah, that's a very good question, and pretty interesting, that article about Sunderland. Bob Gambry goes on to some length talking about how he has better filament control with the cycling air on and off. More often than not, it will improve the control of filaments because you have high dissolved oxygen loving filaments will get killed off when the air is off, and low DO filaments will get killed off when the air is high. Now, returning the solids from the digester back in, it's not been a problem. I'm sure there are cases, but no. Short answer is I don't know of anybody that's had real problems, and probably because if they stuck with it, it wasn't a problem. If it was a problem, they bailed, and I didn't hear much from them. But it'd be interesting to hear if anybody has experiences, good or bad, on that. That'd be nice if you could put something in there for us.
Thanks. And there's a question about using septage as a source for VFAs. Do you think that's a good idea or worth pursuing?
I'm sorry, I was reading the polling at the same time. Could you repeat that? I'm sorry.
No problem. Septage for VFAs. Is that something that has been tried or is worth trying?
Oh, septage is a great source of VFAs. Yes. It's a matter of how it's applied to the wastewater. See, the bacteria that remove nitrates, they will outcompete the phosphorus bacteria any day for the VFAs. And there's others that will too. So if it's in aerobic conditions, the VFAs are going to disappear without any nutrient removal benefit. If it's low oxygen conditions and you put in the VFAs, and there's a high concentration of nitrates, the bacteria that remove nitrates will outcompete the phosphorus. So yes, it's a great source. It's a manner of getting it to the right critters. So there's just some thinking that needs to be done there, or good dumb luck, I guess. Let's see, what do we have for results? Looks like we're pretty much done. So this is great information for me for next week, for all of us putting together or next month, putting together next month's. Looks like a big interest in talking about process control. Okay, glad to hear that. Keep that in mind. What else do you have?
Well, there were a couple of people who were wondering about fixed film processes, a lot of questions specific to their plant, but I just wondered if maybe you could kind of talk generally about that, or if you have any case studies that you might be able to share offline.
Yeah, fixed film, it's pretty hard to do phosphorus removal with fixed film. I haven't really figured that one out. For nitrogen removal, it's very, we actually run a plant, my company runs a plant that has a fixed film anoxic zone to denitrify, to remove the nitrates. So you can create the population for nitrogen removal. I'm not sure how you do it for phosphorus. Should I just, you want to do another one or two questions, or should I just run through my big cities real fast?
Let's go ahead and get the other ones done, and then we'll come back if we have time.
Okay. All right.
Thanks.
Like I said, the only purpose here is to show that big city complicated plants, not really a big city, but 5.5 MGD. You know, the average size of a treatment plant in this country is 300,000 gallons a day. We think of plants under 5 as small. No, they're big. The average is 0.3 MGD. But Kalispell is a very complex plant. It has been doing biological phosphorus removal for some 20 plus years, and it uses the modified Johannesburg process. Look at all these different, these are all different tanks. The former superintendent there told me he had over 1 mile of handrails in his wastewater treatment plant. And what I wanted to show, oh darn, is underneath this banner, unfortunately, is one of the many cells. I think these are number 12, one of these number 12. Some are aerobic, some are anoxic. This plant has always removed phosphorus extremely well. 0.3 is their typical effluent total phosphorus. Nitrogen, really not so good. I think it's around 9. I've got a graph that's going to come up in a moment. For a period of months, they put in a bypass. They took primary, these are primaries. One of these, no, that's the equalization basin. These are 2 primaries. So they took primary effluent, bypassed it around all of these tanks, sent it to this tank here underneath the banner, turned the air off, and used that as a post nitrate removal tank. Did it for about 3 or 4 months just to see. And here's the results right there. So why didn't they continue? Because they didn't have a nitrogen limit. They have a phosphorus limit. They're totally concerned about phosphorus. They discharge into Flathead Lake. And you know, nitrogen wasn't that bad, but look at those numbers by modifying and working with their existing plant. Nashville Dry Creek, a bigger plant. Nashville has, this is Nashville's 2nd biggest plant also for a period of 1 season. This plant, these are the primary clarifiers. These are the aeration basins. There's 6 trains. They experimented with the air on and air off for nitrogen removal in this large plant in 1 train. The way the wastewater flows, these goes through this zone, which is an air off zone. It's actually provides very good biological phosphorus removal. And then it goes through an aeration zone, turns a corner and comes back. So for a period of a few months, this back zone in one of the 6 trains, the air was cycled on and off. Really didn't get anything from that. So then they utilized the step feed equipment, bypassed a goodly portion of flow around the first run of the train, cut back on their phosphorus removal a little bit, but allowed them during that 2 or 3 months that they were doing it, allowed them to get a significant reduction in nitrogen. In my evaluation of their energy use, even you could see a reduction in the blower kilowatt hours. They didn't do it very long because nothing was automated. They had to round the clock have their operators run out and turn valves to open the air and close the air. But this information was used by them and incorporated into their plans for the future for this plant and their larger sister plant, which is Whites Creek, which is about twice as big. Helena, another plant in the 5 MGD range, complex plant in the capital city. They've been very involved in all of this effort. And this is a plant that's got a real nice biological nitrogen removal design. Been very effective for them. They too, they've been applying themselves for years, attending training classes and experimenting with optimizing nutrient removal. They've improved their nitrogen removal by about 2 milligrams per liter. And by trying different things of creating volatile fatty acids in their primary clarifier up here and operating their anoxic zones a little differently, are seeing some improvements in phosphorus removal. We actually came up with a strategy that their design engineers ran through their computer models, and by extending one little pipe through one wall in each of the 3 aeration trains, should get them consistently below 0.5 by their models for phosphorus. So unfortunately, I didn't put the date up there, darn it. So that's my story for today. And I'm sorry to run through those big plants, but we tried to get a lot out there today. I hope there's things of interest. And if there's more discussion, out of respect for people who are on a time, I think I wanted to bring it to a close, but hey, I got nothing better to do than to talk to 950 people who want to listen to me. So if there's more questions or comments, put them out there. And
great, Grant. We'll let those people who need to move on with their day to other meetings and what have you do that. But thank you for granting us a few extra minutes to go over some additional questions that Brendan might have.
Yeah, and I want to encourage everybody, particularly regulators, to tune in to next month. Let's have some discussion about how we move to excellence in the business. But yeah, Brendan, what else do you have here?
There have been a couple of people asking sort of about the limits of what's possible in terms of getting nitrogen, phosphorus through these methods. Like what are the kind of lower limits of effluent concentrations that you've seen?
Okay. Let's put it in context. The context is out of the 150, the best nitrogen I've ever seen is 1. I've seen a plant that consistently got to 1 year-round average. Total nitrogen, not total inorganic nitrogen. So they had a waste stream that's very low in complex organic nitrogen, and they had a very high BOD influent, about 500 milligrams per liter BOD that would drive the D. The best I've seen for phosphorus removal, you got them today. These plants that were designed for it, the Helena plant, or not the Helena, it's the Kalispell plant, and then those 2 plants, the Parsons plant and the Conrad plant. And those were about 0.3. I think Conrad was running at 0.24 for a while for total phosphorus. And again, it's not orthophosphate, that's total phosphorus. Those are my champs.
Thanks. I guess could you also touch on maybe what a facility that's thinking about trying this, what they might think to shoot for, like
Oh, okay. All
a good
right.
expectation for them?
Yeah, that's a great, that's a better way to do it. Thanks. My expectation is a plant should get nitrogen down around 6. That's what I'm hoping for, and a phosphorus of 0.5. Phosphorus, I'm usually disappointed. Very few are there consistently. So we're moving to 1. But 6 to 8 for total nitrogen. Many plants are getting that kind of number. Been doing a lot of work in Kansas, and Kansas, most of the plants are doing pretty well with nitrogen already. So we've been working on phosphorus and extremely happy with the results. I think after 3 years, something like 15 plants have dropped their phosphorus down to right around 1 that weren't before. So I may be exaggerating that a bit, but it's getting pretty close to that.
Thank you. One question is, will biological phosphorus removal work to reduce soluble non-reactive phosphorus?
Yeah, I get that from time to time, and I plead ignorance, because the non-reactive in most all cases is such a small percentage that it's irrelevant until you get well down below 0.5. So I got to plead ignorance on that.
Fair enough.
It's hard for an egomaniac like me, to plead ignorant. There we are.
That is the nitty gritty, as they say. I'm trying to buy some time while I scroll through all these questions.
Why don't we go for about 2, if you have 2 or 3 more good questions, and we'll call it a wrap.
Sure. I apologize. There's a lot to scroll through here. I'm trying to find.
All right, maybe we're.
Yeah, well, let's go with one more question, since I understand it is difficult to get through the logistics of finding the questions to ask.
Well, here's one that's more of a comment, as they say. They say, looks like a lot of the case studies are operating more from a conventional to the extended air mode, i.e. running a high mix liquor. We've added an air on-off strategy with our extended air and had similar success and nitrify year round in a cool climate. So kind of giving you an amen that it can be done year round.
I think that's a good overview statement. Yeah, although there are plants, and I didn't have one. Palmer, Massachusetts comes to mind, has about, I think it's a 9-hour hydraulic retention time and aeration, cycles the air on and off, and is currently running around 5 milligrams per liter total nitrogen. But yeah, many of my case studies have 24 plus hours of hydraulic retention time. But I don't let that limit you. The 9-hour works great in Palmer, Mass, and I suspect 8, 7, 6. Some plants can do good nitrogen removal with shorter hydraulic retention. But that was very astute comment, and nice to hear that they're having success too.
And very last quick one, can you add acetic acid as a source of VFAs for BioP if you're not able to generate it yourself?
Yeah, okay, so acetic acid is vinegar. Vinegar is a VFA. Can you add a VFA as a supplement to drive phosphorus removal? I'm going to give you my suspicion, which is yes. It could be. I suspect it could be very effective. I don't know of anyone doing it. And I would question the cost of it. It's probably cheaper to use chemicals, and precipitate. And something just flashed, so I don't know.
Thank you, Brendan. Thank you, Grant and Laura.
Thank you.
It really was great having your presentation today. And as you saw, we had a full house. We look forward to your final webinar next month. And we will attempt to get you to look at as many questions that have been asked. Hopefully you can get through them. And everyone should see those responses from Laura Paradise, who will mail them out in a couple weeks. With that said, we'll end the webinar. Jake, thank you for helping us with the webinar today and making sure that everything went smoothly. We look forward to having everybody back with us next month, and thank you again.
Thank you.
Jake, you can end the recording.